Good afternoon, everybody, and welcome to our OpenShift 4.3 demo. My name is Ross Beard. I run marketing and alliances at Shadowsoft. Today we'll be spending 45 minutes to 60 minutes going through OpenShift 4.3 demo. A couple of housekeeping items. Feel free to ask questions in the panel to the right. We will likely address these questions at the end. We will be making the slides and recording available after the webinar. And our speaker today is James Jimmy Hendricks, who is Shadowsoft's OpenShift SA. I'll pass the mic over to him in a second, but I did want to spend a couple of minutes just talking a little bit about Shadowsoft and our relationship with Red Hat and OpenShift. So Shadowsoft is a systems integrator based in Atlanta with an office in Nashville. We've been a Red Hat partner for 12 years, and we've been working with OpenShift for 5 years from the early days. And we're seeing a lot of momentum and a lot of companies adopting this transformative technology at the moment. And we're in a great position to help companies in two ways. One, configure, build, and manage their OpenShift platform on Azure, AWS, IBM, VMware, or even bare metal. So this will involve things like cluster management, writing and assisting with OpenShift operators. And then secondly, we're in a great position to help companies integrate OpenShift with their cloud services and other technologies. So things like integrating with Azure's native services around storage, NoSQL databases, functions, and API gateways. We also help companies with their development pipelines, integrating CI/CD with OpenShift. And then a couple of more items we're constantly helping customers with include monitoring, looking at application performance, and then security, things like secrets management, access control, and container security. So on that note, I will pass the mic over to Jimmy, and you can take us through the demo.
Well, hi, everyone. Like Ross said, I'm Jimmy Hendricks with Shadowsoft here. I'm our Red Hat Solution Architect. Today we'll be covering OpenShift 4.3 and some of the new features and navigating through the platform itself. My hope is by the end of this that you all get some general overall exposure to OpenShift and specifically some of the 4.3 enhancements that have occurred between 4.2 and 4.3. Like Ross said, we'll try to address questions towards the end here, given time. If there's anything that requires any deeper follow-up, we'll be sure to address you one-on-one through email or some other form of communication post. So with that, we can kind of jump right in here. So that's me. And so for those that aren't familiar with OpenShift, what is OpenShift? So really what you need to understand is that OpenShift is a secure and enterprise grade platform that is based around Kubernetes that really helps organizations with their traditional or even cloud native applications and workloads. It's infrastructure agnostic. It's designed to work well in distributed infrastructures and hybrid infrastructures, and a number of tools that Red Hat has baked in. Other interesting tidbits is that Red Hat is the #1 contributor outside of Google to Kubernetes, so they're driving a lot of the innovation within Kubernetes itself. So that gives a huge multiplier really around OpenShift's native kind of lockstep around Kubernetes development and feature parity. So for folks that aren't familiar with Kubernetes, Kubernetes is an open source system. It's really a container orchestration engine that is assisting organizations with automating their deployments, the operations surrounding those deployments, and also the scaling and health of containerized applications across multiple hosts and distributed infrastructure. And so there's some things that really drive organizations to adopt Kubernetes. And some of that is around the desire to have self-healing applications and infrastructure, something akin to a failover design, something that will help them orchestrate and manage containers across virtual and physical machines and environments. As well, provide a standardized API for management and development, so that development and operations can work in tandem, that there's uniformity in the development process, and an underlying understanding of really how we're interacting with the engine itself. There's also, again, another standardized command line interface that allows for management and automation workflows. Most of it is in YAML, so anybody who is familiar with leveraging YAML or yet another markup language in long form, it's a human readable format that makes things considerably easier for configuring certain components of Kubernetes. And so again, Kubernetes does a lot for you. Like we said, in those major drivers for organizations adopting this engine is that provides that overall automated orchestration layer. It assists with innovation and driving more enhanced and rapid development, so shortening that time to market by breaking up applications into different containers and microservices. It also makes deployment easier, scaling easier. It can enhance the security within applications by walling off certain parts of an application in its own service. It also provides networking and load balancing plugins and features that make exposing and running applications at scale within a cluster significantly easier, as well as storage. But one of the things that we see with organizations trying to leverage just vanilla Kubernetes is that there's significant challenges in getting Kubernetes up to snuff as far as a platform, really. Kubernetes is a phenomenal, innovative technology that's really helped drive a lot of innovative change, not only in development, but from a process and operation standpoint for organizations. But there are certain components, and especially with third-party plugins that are required to get it into a kind of platformed and hardened form that organizations can really use at scale. So some of these things that Kubernetes doesn't do just on its own out of the box is provide things like multi-tenancy for collaborating and working with multiple tenants and projects, provide native metrics and logging, networking. There's third-party plugins required to establish proper networking, and configuration can sometimes be complex. It doesn't provide a native image registry or CI/CD pipeline or process there. There's no automated build automation for images or dynamic storage provisions. So you can see that out of this list, we've highlighted a few of these that we're going to cover today. And the reason we have done that is because OpenShift really provides the best choice for a Kubernetes deployment as far as a platform and also from a feature standpoint. Some of the interesting notes about OpenShift is that over 1,000 customers are using OpenShift today, and it's been enhanced from over, I believe now, 40,000 support issues from the customer base and developers contributing to Kubernetes and OpenShift enhancements. We had over 17,000 commits to the Kubernetes community itself, as well as over 122 releases of Kubernetes that have been given to the market through Red Hat's enhancements alone. With that as well, there's over 4,000 pods that are deployed per day on OpenShift alone, just kind of lending more to the rapid and wide-scale adoption of this as a Kubernetes platform-based solution. The other thing is that OpenShift and Red Hat have strong partnerships with all of the major cloud providers, as well as CCSPs, so for managed services, and an extensive catalog of certified images to leverage within the platform out of the box. There's also a comprehensive portfolio of different products and services for container management to enterprise functionality, with developer tools, security applications, application management services, storage, and automation. Red Hat has really baked in a lot of enhanced feature sets around Kubernetes to make it more livable and more functional just right out of the box. So one of the things we have to concern ourselves, right, is day one before we can even move on to day two. So some significant changes have occurred between OpenShift 3 and OpenShift 4. One of those major changes is the installation procedure. Within OpenShift 3, ultimately we had to have some underlying operating system established. There was some core OS utilization within existing flavors of OpenShift 3, especially the managed services side. But overall, the installation provider and configuration component of OpenShift 3 was complex. It was driven solely by Ansible, and was often hard to kind of troubleshoot if something went wrong within the installation procedure. Now, Red Hat has made a significantly more streamlined and improved installation procedure within OpenShift 4. In the form of full stack automated installs, otherwise known as infrastructure provided installs, or IPI for short. Part of the advantages here is that OpenShift is now deployed with the minimum viable operating system, Red Hat Enterprise Linux Core OS, or just Core OS for short, and it provides unique provisioners for different infrastructure resources for these IPI installs that are approved. So some folks might have some questions around what is Core OS. Well, again, going back to what I was saying, it's a minimum viable Linux distribution. And so what it's been pared down to is that it's optimized for running the baseline infrastructure components for running those containers. Advantages that it provides there is that because it's a small footprint and owned by Red Hat, over the air automated updates are provided, so you can make sure that your underlying operating system is secure and is stable. The other thing that it provides is a decreased attack surface. With a smaller kernel and a smaller operating system, we reduce our security risks there. It's also attuned to Kubernetes principles and also as well as OpenShift by creating an immutable foundation for OpenShift to run on. And as well as providing ignition-based bare metal and on-prem installation, as well as the cloud host configuration tools and provisioners that Terraform can provide, that Red Hat provides out of the box. So this is an example of an IPI install, just giving you an idea between our control plane and worker node separations. You can see here that the entire process is handled by the installer operators. So all the way from the actual container platform and the cluster services surrounding that, all the way down to the installation of Core OS and the underlying infrastructure resources that are required for Core OS to be configured and provisioned on that infrastructure. So in this instance, cloud resources. Today we'll be leveraging an IPI installed OpenShift cluster on AWS on a few EC2 instances. And we're leveraging Elastic block storage as well as our storage backend. But for folks that aren't in the cloud yet or have a need to split it up in a hybrid format or maybe on-prem first, there's the user-provided or UPI infrastructure install. And so only a few components are really user managed in this instance. One of those would be for our worker nodes. We're going to have to provide some sort of underlying operating system. So whether that be RHEL Core OS, which is recommended, or you can use your existing RHEL installs, as well as for the control planes, your master nodes and our worker nodes. We're going to have to provide the cloud resources in order to provision those to any private or public cloud. A couple of neat components here is that within OpenShift 4.3 coming from 4.2, we're now able to establish private clouds within public cloud providers. If you would like to see any more kind of enhanced documentation around or curiosity around private clouds within AWS, GCP, or Azure, please feel free to contact me after this, and I'll be more than happy to shoot you some notes along what that means for you and how you can go about configuring that. And so with that, we're going to jump into our actual OpenShift 4.3 cluster. And what you can see here is we're in the web console for our OpenShift cluster. What I've clicked into here is just our general home menu here within the administrator pane or administrator view. Something that OpenShift 4 in general has done in terms of separating itself from OpenShift 3 is a slightly refreshed layout of the web console, as well as splitting up two different views and control planes amongst administrators and developers, giving them separate workspaces, and also siloing off developers from unnecessary functionality within the cluster. This is advantageous because administrators need to have an administrative and operational view of the cluster to manage it, and developers need to have their own workspace to request resources, develop with them without getting overladen with unnecessary menu options and so on. So with this, we're going to click into our demo project that we've established for today. Within this, our new project dashboard that's available in 4.3 gives us a number of kind of cool notes and interesting active dynamic dashboards. We can see here within our project dashboard that we have the namespace of our project. So again, projects in OpenShift are handled the same way as namespaces within Kubernetes, with a couple additional feature adds like health checks and monitoring. We can check our inventory of what's deployed, how many pods are deployed, if there's any persistent volume claims, which we'll get into later, as well as the number of services, external exposed routes, the different config maps, and the number of secrets that are contained within that project. We can also see resource utilization here in the center, which is pretty useful from an administrative and day two standpoint, establishing that the project and workloads within that project are healthy, they're utilizing resources in a predictable fashion. And then also resource quotas, which we can get into later. We can see here that we have a healthy, handy dashboard here that shows us the resource quotas we've established in this project specifically and where they currently sit at. So one thing we would do as well when we first get into our OpenShift cluster here is making sure that the health and viability is there. Is it sized properly? Is it up and running? Are nodes ready to receive work? So with IPI installs, we're installing a minimum viable cluster, which usually is 3 master nodes or control plane nodes for high availability purposes and failover, as well as 2 worker nodes. This cluster can be sized up easily through either using the administration or compute sections or by writing operators to scale up the cluster. Here we can see that we're in our monitoring metrics section within monitoring. This is ran by the Prometheus agent on our cluster provided by Red Hat. We can draw on any sort of PromQL metrics, some that are here by default that you can see, some related to the API, some related to Alert Manager, and so on. We can run queries or string them together to get these helpful dashboards out here. And we can even have more advanced dashboards and graphs run through Grafana through the Prometheus UI. Just give me 1 second, folks, to log in here. And if we wanted to create dashboards, we can here, manage them, and leverage all the functionality that anybody who's used Grafana before can provide in tandem with the monitoring agent of Prometheus and OpenShift. So again, this gives you a powerful monitoring tool to leverage right out of the box as an administrator for OpenShift. Other things that are helpful is we also have logs for various components of OpenShift that exist natively. Logging is handled by a EFK stack. So anybody familiar with Elasticsearch or the ELK stack should be pretty familiar with the functionality here with EFK. It's the same thing relatively with Elasticsearch being the database to write any of the logs to. FluentD being our log aggregation daemon, and then as well as Kibana being our visual display mechanism for those logs. So once we've established that our cluster is healthy, once we've established that we got monitoring, we can go into our projects and start creating projects. So again, like I said, projects can be viewed as the same as namespaces with additional feature functionality within OpenShift. This is where developers and administrators collaborate to build workloads, deploy workloads, and manage them. This is important to have projects. This is kind of the multi-tenancy aspect here, as many users and many applications can belong to a project, but projects can only belong to themselves. They cannot belong to another project. So this is helpful for keeping work organized, for keeping all of the areas that administrators and operators would like to pay attention to in a neat, uniform format, as well as giving developers specific workspaces to work within their work set or development projects within. Here we've created this demo project today, which we deployed a simple web app based in Node.js with a MongoDB backend today, just to demonstrate that. So once we built our project, we'd probably want to assign some roles to users that we bring into the system. Users are generally imported in the system through some sort of certification, like LDAP or Active Directory can be brought in to authenticate users, and those users can then be assigned to roles. And so here we can see roles that exist out of the box. Now there's a difference between cluster-wide and namespace roles. With cluster-wide roles, these roles have permissions across the cluster and the ability to interact with different parts of the cluster based off their permission set. With namespace roles, those roles are only assigned to a specific namespace or project within OpenShift. And that's helpful for giving different developers different access within a specific project, or different administrators different permission sets within a certain namespace where they need restrictions or access. There's also system roles, which are more based on the service end. So one thing to understand within OpenShift is that for every workload that's deployed, there's a service attached to it. Because as pods that are running containers within them, being ephemeral as they are and being as transient as they are, need to have some sort of static endpoint that communicate across the cluster and within the cluster, so the applications communicate with one another. These system roles are tied in tandem with the services to provide certain permission sets for those services to act within the cluster. Once roles are created, we can bind them. Here we can take a look at the admin role binding. But for instance, we want to take a look at something like our basic users. And we can see that these role binding has specific differences between what they can do and what groups they belong to in terms of interacting with the Kubernetes API. Going back to roles, we can see that there's a difference here between basic users and admin, because now we can see that within OpenShift, certain things that we call verbs, or basically actionable items that the user can interact with the Kubernetes API on are restricted to things like Git. So in this instance, a basic user is only able to check information, but not update or change information here. Whereas an admin, I have all verbs available to me. Very similar to CRUD operations. So once we get our users into the system, assign roles and the role bindings, we've established some form of role-based access control. We can now go and move on to actually getting workloads onto our cluster. So here we're in the developer pane or view. We can see here that with the already deployed application, I have our MongoDB as well as our Node.js front end deployed. The other deployment you'll see here is Jenkins, the pipeline we use to build that. One interesting thing about OpenShift is that out of the box, it provides two different pipeline CI/CD tools available to you. One is Jenkins that most of us are familiar with in the development community, and the other one would be the new OpenShift Pipelines feature. The OpenShift Pipelines feature that is now coming out of Technology Preview is based on the Knative Tekton project, which is a serverless kind of functions task-based pipeline. So advantages for this that Red Hat has given you out of the box is the ability to establish a CI/CD pipeline without actually having to stand up an independent server for it, versus Jenkins, whereas you would. This is advantageous for a number of reasons. Again, it reduces the attack surface. If someone was able to attack you through your Jenkins pipeline, you no longer have that issue from a serverless standpoint. It also reduces resource consumption because the pipeline is only standing up and operating when it is triggered and then shutting itself down, just like it would a normal container in terms of spinning up and then going away, as well as speed. We've seen significant performance improvements with this type of pipeline deployment in comparison to standard Jenkins. You're also able to use a number of other CI/CD tools that integrate directly into and natively with OpenShift, like Bamboo, for instance, as well if you have pre-existing CI/CD tools. So here we can see our build configs for the applications that we deployed. We can see the pipeline that we established to actually create the build for this Node.js app. Anybody familiar with Jenkins will recognize a lot of this YAML here. And so these build configs tell OpenShift how we're supposed to build our application from an image. Whether that comes from an image stream, whether that comes from GitHub, whether that comes from source to image, or even the catalog that's available, which I'll show here. This is another interesting point of OpenShift that Red Hat gives you out of the box, is that there's a developer catalog of existing apps, services, and source to image builders that are available to you, again, out of that box. So these make it significantly easier to move onto the platform. What's also interesting is that Red Hat has tied in all of their middleware solutions into OpenShift through their catalog to be able to be easily deployed within the cluster and containerized. This is advantageous because it shortens the adoption time as well as the enablement time, or I guess we say the time to spin up on getting used to the platform. There's also some advanced functionality within the developer pane here. We don't have to really go too far into that, but the project details are the same as the project dashboard for administrators. Again, giving that overall view. Keep in mind, these menus can actually be restricted based off of the role, if so desired. So again, controlling who can interact with what and what information they have access to is highly advantageous, especially in a multi-tenant environment. So once we have our applications and workloads deployed successfully, there has to be a couple of questions we need to answer. One, are our applications stateful? In many organizations, we notice that they're deploying applications onto the cluster that require statefulness, which means they'll require some sort of persistent storage. This is a challenge because Kubernetes natively is kind of organized around stateless applications, often found in cloud native environments, whereas a lot of traditional workloads that organizations are breaking out into microservices or containerizing still require some form of statefulness. So again, the persistent storage solution is required. Again, Red Hat provides an out-of-the-box solution for this with OpenShift called OpenShift Container Storage 4, or OCS for short. You can see here in our dashboard for our projects here that we have an OpenShift Container Storage persistent volume area where we can check capacity, the utilization, as well as certain metrics associated with that storage, as well as object services for object-based storage. Going back to our presentation, OpenShift and Red Hat provide really a wide array of native storage class plugins that aren't natively available right out of Kubernetes. So this is advantageous for a number of reasons. One, it allows you to use persistent volume frameworks immediately out of the box and configure that persistent volume to your needs, to the statefulness of your apps. The other thing is that this list is constantly growing. So again, Red Hat is increasing the native functionality around storage and storage endpoints for users. So the native solution for OpenShift Container Storage is Ceph. Those who are familiar with Ceph, great. If not, a good explanation here is that, well, Ceph is a object block and file storage system that's highly resilient. It's extremely fast as well. So this is great for users who need something with a high failover capacity, and also someone who may need persistent volume storage across multiple clusters or environments. So Ceph is a great solution for that. So this is kind of an overview diagram of how persistent volume consumption occurs within the cluster. We would establish what we call a persistent volume claim, this little YAML file down here, and the persistent volume specified as well here. We can see that the claim name for the persistent volume claim is Z in this example. Someone makes a claim to a persistent volume we've established. In this case, it'll be OpenShift Container Storage. Now we're using Elastic Block Storage today in this cluster. That persistent volume object for the storage operators communicates with the actual storage part of the API, which relates to the actual pod and containers that are claimed to that storage, being able to leverage it. So a couple of notes of difference here is that there are two ways persistent volumes can be provisioned within OpenShift. One is statically. So a cluster administrator can create any number of persistent volumes, and they carry the details of real storage and will be made available for use to cluster users. They exist in the Kubernetes API and are available for consumption as resources as needed, given there's probably going to be some sort of persistent volume claim resource limitations that administrators would leverage per project. This is helpful because, obviously we don't want developers being able to just request all the storage in the world for one project, right? The other type of provisioning is dynamic, and this is one we'll probably see more use of. So when none of the persistent volumes that an administrator has created can match a user's persistent volume claim, or PVC for short, the cluster can try and dynamically provision a volume specifically for that claim the developer's making. That provisioning is based off of something called storage classes. So a couple slides earlier, I showed you a couple of the storage plugins. Those are native existing storage classes within OpenShift today. And so the PVC will request a storage class type. And again, the administrator must have created that specific storage class and configured that to be able to dynamically provision to. The claims request that class, and they effectively dynamically provision themselves to that persistent volume. So recovering that, developers can make a persistent volume claim that allows them to consume storage resources. It allows them to leverage persistent volumes with varying properties, such as performance, for different types of workloads, speed, and so on. And persistent volume claims can differ in more ways than just size and access modes. What this really helps is with developers, when they're making these claims, they don't really have to understand the underlying infrastructure. They just need to know that they're going to have resources available for their application to run properly. So this removes a lot of the, I guess, headiness or level of details the developer need to concern themselves with underlying infrastructure, and allows them to solely innovate and run and develop applications without having to concern themselves again with all the nitty-gritty details they might have had to use in prior types of architectures or systems. This is a good example of the dynamic storage provisioning here. So again, dynamic provisioning allows provisioning of persistent volumes on demand when users request it through the PVCs, rather than having the administrators or operators define those in advance. And that storage class, again, just think of it as a blueprint of how to provision the persistent volumes on network storage. So moving back into our web console here. Now that we've established some form of persistent storage, and just to give you an idea of where you can deploy OCS for, is you would go to the operator hub. We could go down here into storage or search, and you can see OpenShift container storage is an option here. And let me just touch on operators for a second, actually, because this is another thing that's very important for us to understand within OpenShift. One of the biggest dynamic changes as well between OpenShift 3 and 4 is the operator framework. Now, those not familiar with operators, we can really think about them in this way, is that they're codifying human operative knowledge or human automation knowledge into something that the Kubernetes API can use. And one of the advantages of this is that previously updating and maintaining containerized applications were traditionally manual processes, and that obviously becomes tedious, it becomes cumbersome, and it also opens up your system to vulnerabilities if certain things aren't watched and patched in time, right? So Kubernetes operators really change the game in this regard, because the operators extend Kubernetes to help streamline and automate that process from installation to updates and management of container services. Operators do this through leveraging two things, which is a custom resource, so what the operators are acting on, and the custom resource definition, so what we're defining as the custom resource and the behavior associated with the operator attached to it. And then that operator acts in a continual feedback loop to consistently watch that object that it's associated with and ensure that it's in the statefulness that it needs to be within. So you can see that this is kind of a helpful automation tool across the cluster to do things like provisioning OpenShift container storage and subscribing to a certain update pathway there, and ensuring that that's always up to date and that your persistent volumes are stable. But operators can also do things like continually check the cluster for pods to ensure that they're in ideal states, to bring pods outside of their desired state into the ideal state. And what's really helpful here is that in this instance that I'm using, like for stateful applications usually have pretty strict protocols that are associated with them that ensure functionality and stability. So operators really allow users to interact with complex distributed applications across the cluster by way of making them feel like a unified application and wrapping them inside the CRD components. Other things that operators allow you to do is they allow you to update core and supplementary components, such as like the host OS, so patching core OS, as well as scaling infrastructure. So setting up infrastructure operators to scale up machines, get them ready to be deployed as new nodes, as well as upgrading OpenShift itself. So now we've gone through a number of things from pipelines to persistent storage and volumes, persistent volume claims, as well as how do we get workloads onto our cluster. Now that our workloads are on there, we need to concern ourselves with services and routes. So going back to that instance that I told you about with services, again, services are the static endpoints within the cluster that applications and workloads are tied to. Pods have temporarily assigned IP addresses within the cluster because they're ephemeral in nature and spin up in terms of level of demand and configuration. The workloads associated with that have to have some sort of static endpoint that the API can talk to within the cluster, and other applications that might need to communicate with it can talk to as well. So you can view this as like an internal route within OpenShift. But what happens if we need to, let's say, have an application be available to customers outside of our cluster, or have it be available to people within our organization as an internal application? This is where we would expose our applications to the outside world through the use of routes. So the router operator helps act on the router that's built into OpenShift and provides native networking functionality to allow you to easily expose applications to the outside world and allow people to access them. In this instance, I can demonstrate that we can go to our Jenkins pipeline that we've established earlier, that we deployed within our cluster, or in this instance, the Node.js app that we deployed will take us here. This is just kind of a little helpful cheat sheet and directory for helpful OpenShift documentation and processes. So you can see here that Red Hat has included a lot of powerful networking tools that aren't natively available or easily configurable within vanilla Kubernetes to make life easier, deploying workloads easier as well as more stable, and overall just make your day-to-day process as an administrator or an operator significantly more lightweight. You can also, if you're familiar with Kubernetes Ingress, use the Kubernetes Ingress module within OpenShift for traffic. You can also establish network policies for different namespaces as well as for the entire cluster. You can also bring along other load balancers too. OpenShift comes with its own native load balancer out of the box, but if you wanted to use something like F5, for instance, you're more than welcome to bring your own load balancer. So let's say you've done your IPI install. You need more infrastructure, though, to run your workloads, which means you need to bring up more nodes to handle more applications, and maybe even bringing up infrastructure nodes. So we can see here we have our nodes. Now, nodes within OpenShift is any instance where there's an underlying operating system attached to it. So in this, you can view it as like an individual machine, or like almost view it as like a VM, if you're familiar. So each one of these nodes that are operating right now have its own core OS attached to it currently. We have our master nodes, which is our control plane, and then our worker nodes. I've spun up 2 additional worker nodes here, and you can see that their names are based off of whatever naming convention is generally provided by the underlying provider. So in this case, you'll see EC2, you'll see regions and zones as well within the machine names that are specific to AWS, because that's what we're deployed on today. Now, what's the difference between machines and nodes, you might be asking yourself? Machines are nodes that haven't been deployed yet, or they're configurations of nodes we wish to deploy. And we can define those machines. So let's go into one of our worker nodes, for instance, and look at a machine configuration. We can see the type of infrastructure we wish to deploy it on, the API interaction will have with Kubernetes, the type and role of that node, so we can give it labels. This is useful for distributing workloads to specific types of nodes. So in this instance, for worker nodes, we typically would want to run our applications on the worker nodes and maybe create infrastructure nodes for running things like the router or storage on. We can see the instance types as well as the credential secrets that we would input here to provision them on the infrastructure. And a number of tags to help identify what this machine is and its functionality. Now, machine sets are configurable files that allow us to establish a configuration around how many or the number of machines we wish to be brought up. If we go back to the nodes that are deployed, pay attention to looking to this region 1C here. We can see that there's 2 deployed as specified in the machine sets that I've had here. So a machine set is directly akin to a replication controller or a replication set with an OpenShift that is specific to the number of pods that should be deployed for a specific workload. This is where we establish, again, the number of machines we'd like deployed per type of machine. We can see here that we have 2 replicas, as well as selected regions and zones, and the instance types. This gives you a high degree of control over a number of things, but mainly just over what and where your nodes are going to be deployed. And this gives you an advantage of making sure that your infrastructure is resilient, your cluster is resilient as well. You can also establish autoscalers based off of demand. And so through the traffic and the Kubernetes API, we can set minimum and maximum replicas that are established based off of a certain type of condition set. We're not going to generate one today, but if you have any curiosity around how to use autoscaling within OpenShift, I'm more than happy to walk through with you on a one-to-one basis on that. Once we have all of our infrastructure up, we can go back to metrics and alerting. So one thing that's great is that OpenShift comes with its own native alert manager agent. There's a number of default alerts that are already established within OpenShift, which is very helpful. But you can create your own custom alerts to alert you to certain aspects of whether that be the infrastructure itself within your cluster and health, or actual specific workloads to alert different people at different levels or different roles to be made aware of when things are not well, or when something is not in an ideal state, or even if something has been running for too long, something along those lines. You can create any number of alerts, and you can also group those alerts together. Here you can see some of the default ones and some that have fired already. For instance, a pod not being ready to take traffic once it exceeds a non-ready state for longer than 15 minutes. One other helpful thing too is, again, going back to compute, either through leveraging the compute menu or through infrastructure operators, we can create and delete machines and therefore reduce the number of nodes running, which can help with consumption. Oftentimes we'll see people set up auto scaling or period auto scaling for, either whether that be seasonal or like time of day based burst demand. So for those who have maybe like e-commerce during Black Friday, this would be something where we could set up a time-based auto scaling. Or for those who maybe operate something like Uber Eats, we could set up auto scaling for lunch and dinner time, for instance, to ensure that we're meeting demand. So with that, I'd like to open up some questions to everybody, if they have any right now.